Welcome to this video tutorial on data types in automation system. In this session, we also compare different features and capabilities of different type of PLCs of Siemens. There are 8 columns in this table representing 8 bits in a byte. This slide explains how an input bit is addressed in the process input image of a PLC. The notation 3 I 3.4 means I stand for input byte, input area, 3 byte number, and then dot, then 4 means bit number. This slide demonstrates how input and output bit is addressed mapped in the process image of a PLC. The notation Q 3.4, 3.7 refers to Q output area, 3 is a byte, 7th is a bit position. This means that 7th bit of a output byte 3 is addressed. It is a part of process output image which is cyclically updated during each scan cycle of a PLC. In Siemens PLC, M refers to memory byte, memory area, B for byte. When referring to the word value 16 bit, it consists of 2 bytes. MB 100 most significant byte, MB 101 least significant byte. When referring to 32 bit, it consists of 4 consecutive bytes. MD 100 means it consists of MB 100 most significant byte, MB 101, MB 102, and MB 103 least significant byte. Let's take an example of analog input. Analog value in PLC typically of 16 bit, 2 byte long. The PLC converts real world analog signal such as temperature, voltage, and pressure into 16-bit digital value that can be processed with the program. Similarly, output of the PLC consists of 16-bit digital value into a corresponding voltage and current signal, which is proportional to the digital value and can be used to drive actuator and other device. Both timer and counters use 16-bit word value for the current value. The special feature in that timer T3 tags behaves as a digital bit when used in logic conditions and as a word value when monitoring in the time process. When timer T3 reaches its preset value, the T3 bit becomes 1, which turns the Q3.1 on. In the following example, every time input I2.1 is switched on, it increments the current value timer T3. Once the current value exceeds the preset value, T3 bit is set and the output condition becomes true. The current timer value is stored in the memory word MW50, which can be monitored in the real time. In this example, the current C3 value behaves similar to the timer in terms of 16-bit word value. The counter C3 acts as a digital input when counts reaches the preset value. At that point, C3 turns on and energizes the output Q3.1. In the following example, when the input I2.1 transition from 0 to 1 rising edge, it increments the current value of a counter C1. Once the timer exceeds the preset value, the counter bit C3 becomes active, logic 1. The current value of the counter can be observed in memory word MW50, which reflects the current count. When the input switch is connected to the input I3.4 is pressed, the status is written to the process input image PII. Once the input device sensors update their values in the PII, the PLC needs the entire input image. The scan time refers to the duration of the PLC takes to read the input of the PII, execute the user program, and write the result on the process output image. Update the actual outputs. In this example, After processing the input, PLC will turn on the output Q2.6, lighting the connected bulb. This table compares the S7200 and S7300. Here we can see that V memory is available in S7200, but in S7300 DB and other instance DB, shared DB is there, and SM special memory is there in S7200, and we will see later how we can manage S7300. PIW stands for the peripheral input words and PQ stands for the peripheral output word. They are a part of peripheral addressing, which allows direct access to the input-output module by passing the process image. The key difference between S7200 and 300 is S7300 use special memory and B memory, and 300 DBs are used process input image. Concept of IO is also there. More powerful is functional blocks FC, FB, OB of the FC for functional functions, OB for organization blocks, and structured programming in F300, S7300. Here we see the S7200 special memory, SM0.0, SM0.1. SM0.0 is always on. For when we start the PLC first scan, it will give a pulse SM0.1, and this is a clock memory. One hertz clock pulse is there. If you want to blink the light for 1 hertz, then we use this SM0.5, SM0.6 for 0.5 hertz clock and different. But in SM300, I will discuss it later. In S7300, we open hardware configuration, then CPU properties, then we go to cycle clock memory, enable the clock memory, assign byte. If we use M0 of then M0 dot 5 becomes 0.5 hertz. Different types of clocks can be achieved by this. The same thing can be achieved by S7300 also, as we get a special memory in S7200. This table presents various data types used in automation, such as integers, real, double word, along with their value ranges. Timer format is S5T hash. Then we write hours, minute, seconds, and different type of timers is also available. T on delay timers is there, T off delay timer is there, pulse timer is there, TP. S7 200 uses microwins software, supports subroutine and limited input output, but has a limitation of getting pooling input and output maximum to 16. Basic PID supports, but in S7300 we use semantic manager. Global DBs and instance DBs are there for storage, and FBFC functional block for functions, special function blocks, special functions, and OBs or organization blocks is there. In SM300, 400, 1200, and 1500, TIA portal is there. Unified programming protocol for newer Siemens PLCs, advanced diagnostic libraries, and better UI integration. Thanks for watching. If you found this video helpful, please like, subscribe, and hit bell button for more tutorial on PLC and industrial automation.